So what we're going to do in this problem is go over how to tackle an optimization problem, and we're going to use this example that we have from the book. So the example says a rectangle is bounded by the x and y axes, and the graph of y equals 6 minus x over 2. What is the length and width should the rectangle have, or what length and width should the rectangle have so that its area is a maximum? So before you do anything at all, try to know what you're solving for. What is the question asking you to do? So if you look at the very end of this, it says what length and width. So we have a length and a width. We have two answers, a length and a width. And based on this graph, it looks like we might have an x coordinate and a y coordinate. So the rectangle has, so its area is a maximum. So if we hear area is a maximum, that means we are maximizing area. That sounds pretty straightforward. That is what you are trying to do. That's your main objective. Now that you know what you're going to tackle, then you can start asking yourself these questions. So your first things you're going to ask is, what's the primary equation here? So the primary equation is generally what is going to describe our main topic, which is the area. So our primary equation here is going to be like, okay, if we're trying to maximize area, how do we define area in an equation? So this rectangle right here has an area, right? And it's length times width. Well, what defines our length? So let's say x is our length and y is our width, correct? And that's valid. We can say these are our length and width, and if we multiply them together, we get an area. So area is equal to x times y. So that is our primary equation, and that's what we're trying to maximize. Now, the thing is with that is that it's two variables, and that's an issue. So let's go on to step number 2 before we start getting to step number 4, which is simplify to one variable. So we have to find a secondary equation. So secondary equation is generally either found based on what the question is telling us, like a secondary information that we have, or it's just given to us straight up. So we have y is equal to 6 minus x over 2. That is considered a secondary equation. We can use that. So and it's important information as well. So it's y equals 6 minus x over 2. This can be very helpful. Then we got to find the domain. So how long can x be and how short can x be? So we have the x-axis, the y-axis, and then we have this line right here. So as y, the highest y can be in this scenario is 3, and the lowest can be 0, and the highest x, or the lowest x can be is also 0, the highest x can be 6. So this is the area that we're dealing with. This is under this rectangle. So x is in between 6 and 0, and y is also in between 3 and 0. So this could be important information. This also helps you to know that, like, if you get an answer outside of this range, then you know you did something wrong. So this helps. Number 4, simplify to one variable. So we got to simplify this equation, a is equal to xy, to one variable. So how? So we have a secondary equation, correct? We can use this information to basically create this equation to one variable. So we have y is equal to some function, or y is a function of x. So it has y equals 6 minus x over 2. We also know that area is equal to x times y. So, well, what if we plugged in y into this equation, right? So we might get area is equal to x times this equation right here, the secondary equation. So we get 6 minus x over 2. If you simplify that, you just get 6x minus x squared over 2. So that's just a different way to describe our area. Then we can actually solve for the maximized area through basically the first derivative test and the second derivative test. So in order to do that, we have to find our critical points. So first we take the derivative of this function. And can we do it? Yes, because it's only a variable. The only variable we have is x, and we don't have xy. So we can do this. So if we do dA dx, which is the change of the area with respect to x. So as x changes, how does the area change? We get the derivative of this, which we get 6 minus 2x all over 2. And then we can set this equal to 0 in order to solve. So then we just multiply by 2 on both sides if we wanted to make it simpler. We got 6 minus 2x is equal to 0. So that means 6 is equal to 2x. That also means x is equal to 3. Now we can use the first derivative test in order to start solving for this. So we can do it where we know that as we can look at this equation right here and we say like, okay, as x, you say as x is equal to 3, this whole thing is equal to 0, correct? Right here, sorry, my bad. As x is equal to 3, this equation is equal to 0. Well, if we increased x, so we have this line, and x equals 3, this equation right here is equal to 0. If we increased x, like say to 4, we have 6 minus 2 times x, which is 8. That's a negative number, so that's negative. If we decreased x, we get 6, say for example x equals 0. We got 6 over 2, that's a positive number. So based on our first derivative test, this looks like a relative maximum. We can also check a second way by doing the second derivative test. So if we do the second derivative of this equation, we get d squared a over dx squared. This is going to tell us the concavity of this. So that will just equal negative 1. So that means this equation always has a concavity of negative 1. And when you have a negative number, that means it is concave down. So this graph looks something like this all the time. And since we found that x equals 3 is a critical point where the derivative was equal to 0, so the tangent line is also has a slope of 0, this is a relative maximum. So this is our maximum basically value for x. So we know our x coordinate is equal to 3. Well, what about our y coordinate? Because remember, the question asked us for a length and a width. So we can actually use this equation again to find y, right? So if we go here, right, we got y is equal to 6 minus, and then our x value, which was 3 over 2, which is equal to 3 over 2. So our coordinates now is 3 for x and then 3/2 for y. So if we look at our problem here, that means when x is at 3, x equals 3, and y equals 3/2, which is 1.5, right? That gives us our maximum area that we can possibly have as long as it's bounded between y and x and this line.